All right. Welcome to Essentials Physics Video 2.5, which is the same as Physics Video 3.8. We're going to learn about the basics of Newton's third law. We will be seeing some demonstrations and whatnot of this in class. So this is basically just kind of designed to teach you a very simple skill. This is going to sound weird, but try not to think about it too much. And we'll have some sort of more meaningful discussions about it after you've watched this video. All right. So here's the objective today. You are going to be given an interaction between two objects, and based on that, you should be able to describe what the action and reaction forces are. All right. So here we go. Before we learn about Newton's third law, I need to emphasize a really important fact about forces, and that is this: every force in the entire universe, without exception, has two objects associated with it. Okay, so here's the two objects. The first object, or one of the objects, is the object being pushed or pulled. When you make a free body diagram, that's the object that you draw. And the other object is the object doing the pushing or pulling. When you make a free body diagram, that's how you label the forces. So, as a simple example, suppose I told you Roy pushes a box. Okay, the two objects are Roy and the box, right? The object being pushed is what you draw. You draw the box, right? And you would write down the mass inside. And then when you label it, when you say Roy is pushing it, you label it with an arrow and you go, oh, here's the force of Roy. So when you make your drawings, you're indicating the object being pushed and the object doing the pushing or pulling. Okay? It is tremendously, super, mega, colossally, galactically important that you are able to identify both objects, okay? And I'll be honest with you, in most cases, it's super easy, right? Like in this case, Roy pushes a box. Well, duh, the two objects are Roy and the box, right? But sometimes it's not so clear, all right? So we're going to run through a couple examples. We're going to start with easy ones and then work our way up to ones that are a little bit more difficult. All right, so in the first one, Carl pushes a box. Actually, tell you what, take a second, pause the video right now and see if you can figure out what the objects are here. Okay, I'm going to assume that you've done that. So in number one up here, the two objects are Carl and the box, right? So no big deal with that, right? In the next one, a table prevents a box from falling. So you've got this box that's sitting there, and the table is holding it up, right? So once again, I think fairly straightforward. Your two objects are the box that's not falling, and it's not falling because the table's pushing it, okay? 3 is kind of the same thing. The ceiling prevents a helium balloon from floating away. So you've got this helium balloon, it's trying to float away, but the ceiling is pushing it down, preventing that from happening. So there's your two objects. Number 4, to be honest, if you put ball and roof, I totally understand why this is worded badly. I should really correct it. It's talking about the ball falling, okay? So why is the ball falling? Because of gravity, right? So hopefully you identified one of the objects as the ball. The roof actually doesn't have anything to do with this because the ball's not touching the roof anymore, right? It's falling off of the roof. So why is the ball falling? And the answer is because of gravity. So a lot of people then will say, oh, well, your second object then is gravity. But the problem is that gravity is not an object. Okay, so we can't count that as our other object. So now we got to figure out, where does gravity come from? And the answer is the Earth. It's the Earth's gravity that pulls the ball down. So this interaction, anytime you've got an object falling, anytime you're talking about the force of gravity, then your objects are whatever it is that's being pulled by gravity, and the other object is the Earth, because it's the Earth's gravity that pulls the ball. Okay? In the next example, a baseball player slides to a stop. So hopefully it was clear that one of the objects is the baseball player. Why does he slide to a stop? Well, picture that. He's running. He slides into base, right? Very exciting. What's causing him to stop? Friction, right? So, but once again, friction isn't an object. It's not something you can physically touch. So friction is not an object. All right, so what is it? It's friction between the baseball player and the ground or the earth or whatever. So our second object here would be the ground or the earth. I'm going to write earth just because it's a shorter word than ground. You could say dirt, whatever. But you got to pick a physical object that you can touch. And neither gravity nor friction are physical objects you can touch. All right. excuse me. The last example here is kind of a silly one. A magnet sticks to a filing cabinet. So you've got this magnet, the filing cabinet is attracted to it. So your two objects are the magnet, oops, and the filing cabinet. Okay, so anyway, that's got to be your first step. When you're doing a Newton's third law problem, your first step has to be figuring out what those two objects are. Okay? Excuse me, I'm sorry, I'm so sniffly. All right, so here's what Newton's third law says. It says, for every action force, there's an equal and opposite reaction force. Okay? For every action force, there's an equal and opposite reaction force. So it's the forces that are equal here. All right? In simplified terms, it's this. Anytime object A pushes or pulls object B, okay, so you've got two objects, object A and object B. Anytime object A pushes or pulls object B is going to push or pull object A with an equal amount of force in the opposite direction. Okay? So, here's what that means. Suppose you've got an action force. Object A pushes object B forward. Okay? Your reaction force then is going to be object B pushes object A backwards. So, action, A pushes B forwards. Reaction, B pushes A backwards. All right? So the idea is, in most of these problems, what's going to happen is you're going to be given an interaction, and you're going to figure out what your action is. Okay, so it'll be object A pushes object B in a certain direction. Okay, your reaction, all you're going to do is you switch your two objects. Okay, instead of A pushes B, it's B pushes A. So these guys get flip-flopped, right? So instead of A pushes B, it's B pushes A. Your verb is still the same. If this was pushes, this is pushes. If this had been pulls, then this would have been pulls. And then your direction just changes. So instead of being pushed forwards, it's pushed backwards. If this had been up, this would have been down. If this had been north, this would have been west. Okay? So, a couple important things to notice, and I just said this. First of all, if the action is a push, the reaction is a push. If the action is a pull, the reaction is a pull. Okay? Next, the action and reaction occur simultaneously. The entire time these two objects are in contact or interacting with each other, they're both interacting with each other. So as long as object A is touching object B is also touching A. Okay? Which force is the action and reaction? Doesn't really matter. So they're interchangeable. On this problem, I made this the action and this the reaction. I could have flipped that, and it doesn't matter because they happen simultaneously. All right? One other thing that I should have typed here is that they're equal and opposite, so that your action force, your force action, right? That's action, A-X-N, action, is equal and opposite to the force reaction, all right? Eventually, you're going to get questions that'll say, you know, identify your action and reaction, and then it'll say, which of these forces is bigger? And it's a trick question, because they're equal. That's what Newton's third law says. It says the forces are equal and opposite. All right, so watch out for that. That's something that people mix up often. Okay, just to kind of get you thinking in the right direction, there's going to be a question on a homework assignment in a couple days that'll say, you know, Roy punches Carl in the face. Is the force bigger on Roy's fist or Carl's face? And it turns out they're the same. Okay, so we'll talk about that and why that's weird. I said earlier in the video not to think about it too much, so I guess I should stick with that. So we'll talk about that more later on. But anyway, for now, just remember those two forces are equal, and we'll talk about the why later on. All right? So for now, basically, here's all we're going to do. I'm going to give you an interaction like this. Carl pushes a box. You've got to identify both the action and the reaction. Okay? So pause the video right here and see if you can figure these out. Okay? So for your first one, hopefully you've paused it now. For your first one, it's this. Your action is, it pretty much tells you, right? Carl pushes the box. So your action is the force of Carl pushes box forward, right? So there's your action. So to find your reaction, you switch the two objects and change the direction. So it's the box pushes Carl backward. All right? So if you got that first one wrong, what I'd like you to do now is pause the video again and try these again. Okay? So here we go. Table prevents a box from falling. Okay, so there, the table's pushing the box up, right? It says the table prevents the box from falling. So that's what's happening, is the table is pushing the box up to prevent it from falling, right? So your reaction then would be that the box pushes the table down. Think about that. If you've got a box sitting on a table, two things are happening. The table's pushing the box up to prevent the box from falling. But because the box is sitting on the table, its weight is pushing the table downward, right? If you put a really, really big box on the table, there's going to be a lot of pressure from that box pushing the table downward, right? So that's what's going on there. All right. If you got that one wrong, pause it again and see if you can revisit 3 and 4, okay? So here we go. For number 3, a ceiling prevents a helium balloon from floating away. This is really similar to number 2, okay? So here we go. Your action is the ceiling pushes the balloon down, right? That's why the balloon's not floating away, because the ceiling's pushing it down. So your reaction then would be that the balloon pushes the ceiling up, right? Okay, if you imagine a really, really big balloon, the balloon would be pushing up on the ceiling, and maybe it could break through the ceiling. You're probably not picturing that, it's a smaller one, but that balloon is pushing the ceiling up. All right, one other thing I should comment on here, just to reiterate, is that these are interchangeable. So I could have, on any one of these, if I'd wanted to, switched my action and my reaction. All right. For me, the way that I've got them listed sort of seems a little bit more intuitive, but really it doesn't matter. Okay. So, ball falls off a roof. We talked about this one. Let's try it. So before we do, again, what are the two objects? The ball and why is the ball falling? Because of gravity. Gravity from I need an object. The earth, right? So this one is really weird. And again, try not to think about this too much. And we'll talk about it a little bit more after you've watched the video. But so here's your action and your reaction. The action is the earth, or the earth's gravity, pulls the ball down. So remember, to find your reaction, just switch the two objects and change your direction. So your reaction is the ball pulls the earth up. Okay, and that's actually correct. We will learn more about this later on. Gravity is actually very similar to magnetism. And if you picture two magnets, they both pull on each other, right? This is the same thing. In the same way that the earth pulls the ball down, the ball pulls the earth up. Now, just because the ball is pulling the earth up doesn't really mean that it moves any significant amount. Technically speaking, it moves a teeny bit, but not enough that you'd ever notice it, because the earth is freaking big, right? It's really, really big. And so the ball pulling the earth up does not provide enough force for it to move any appreciable amount. Okay, so again, don't think about it too much. Just remember, if A pulls B, then B pulls A. If earth pulls the ball pulls the earth. And just leave it at that for now, and we'll talk about it more in class, okay? All right, we got one more slide, just a little bit more practice on these. Again, pause the video, try these. I'm going to just throw all of the answers up here because I'm running a little tight on time. No, that's not a good idea. We're going to go through them one at a time. All right, baseball player slides to a stop. Here we go. Oh, what are the two objects? The baseball player and friction's not an object. It's the earth or the ground, right? So the action is the earth pushes the player backwards, right? The player's running forwards, presumably. When he slides, he slows down and stops because friction from the earth is pushing him backwards, right? Preventing him from moving forwards. If a drawing helps, it's this. Oh, if a drawing helps, it's this. Here's your baseball player. He's got to wear a hat, right? Right, so he's running this way. And when he hits the ground pushes him that way. So there's the force from the ground. Or force from what I called up here, the earth, I guess I should say, earth. Okay, so there's your action. So for your reaction, just switch your two objects. So your reaction is going to be the player pushes the earth forwards, right? Which is why there's a giant cloud of smoke, right? Or not smoke, dust and stuff, right? When you slide into base. Cool. All right, a couple new ones here. This is kind of weird. Roy takes a step forward. All right, think about what you do when you walk. When you walk, what are you pushing on? The two objects are Roy, or Roy's foot, and the ground, right? So there's your two objects. So when you take a step, you push the ground backwards. So Roy pushes the ground backwards, right? Think about that. You've all done this before where you step on a rug or something that's not firmly attached to the ground, and you take a step and the rug slips out from under your foot. It's because you're pushing it backwards, right? And so then the reaction is the ground pushes Roy forward, right? Okay? And that's how he moves forward. A car driving is the same way. When the wheels spin, they push the ground backwards, right? Which is why rocks and stuff can shoot out behind a car. And the reaction is the ground pushes the car forwards, all right? Okay, I'm going to just fill in these last two. The last two I think are a little bit more straightforward. Tomorrow, or when I see you next in class, you're basically just going to be kind of practicing this, okay? Oh no, the bell has rung. Okay, so for the last two, when the goalie catches a ball, if the ball is moving towards him, then when he catches it, he's going to push the ball forwards, right? And the reaction is the ball is going to push the goalie backwards. All right, and in this last one, if you've got a cabinet pulling oh, shoot. This was wrong. I should say magnet. So the magnet pulls the cabinet back, and the filing cabinet pulls the magnet forward. Again, these directions are sort of arbitrary. This could be, right, and this could be left, or whatever. Okay?